So far we talked about various advanced materials. We talked about nanocrystals, we talked about glasses, we talked about quasicrystals. We also talked about nanocomposites. For example, nano quasicrystals in an amorphous matrix or nanocrystals in an amorphous matrix. So all kinds of nanocomposites we talked about. So from today, for a few lectures, we will talk about the processes which are used to make these advanced materials, or what we call them as novel materials, because many of these have much different properties than the conventional materials. So we start with one of such processes called rapid solidification processing. As the name suggests, this is nothing but solidifying it rapidly. We know solidification in metallurgy very well. So we take a liquid and allow the liquid to solidify very rapidly and try to see what kind of new microstructures, new type of materials that we can generate by this rapid solidification processing. As I told you, so far whatever novel materials that we have discussed, such as either glasses or nanomaterials or quasicrystals, these are all, as I informed you before, that we can generate them from all the three states of matter. We can generate from starting from the vapors. You can take vapors, condense them, and you can get a nanocrystal, or you condense them, you can get a quasicrystal, or you can get a glass, depending on the conditions, depending on the system. Everything depends on that system, the thermodynamics of the system, the kinetics of the system. So, but it is possible to have all three from the vapors. One can generate quasicrystals also from the crystals. If you choose the composition properly, that it corresponds to the quasicrystalline composition, you can generate vapors and condense the vapors and get a quasicrystal. Similarly, you can get nanocrystals. We have already talked about it when we talked about nanocrystals. And amorphous, many people have done thin films of amorphous by depositing the vapors. In fact, whenever you deposit vapors as thin films, most of the time you get only amorphous. It depends on the thickness. The thinner the film is, the more, the easier for the glass formation. Usually, when you look at very thin sections, they are usually amorphous, because in thin sections the solidification rates are very high. Whenever you are condensing the vapors also, it's basically cooling rates that matter there. Similarly, the second route is from the liquid. As I told you, you can take a liquid and from liquid cool it very slowly under equilibrium conditions. You get the equilibrium microstructures. You cool it slightly rapidly. Then, depending on the type of system and depending on the conditions of cooling, you can get any of these novel microstructures. Today we will talk about that. Then the third route is what is called the solid state route. You can take the solids, and then those solids you can convert the conventional solids into any of the structures. For example, you can take a crystalline solid and introduce defects into it by any means and then make it into amorphous. We have talked about that. Then we can take a crystalline solid and break it into smaller and smaller size and then make nanocrystals out of it. That is one technique which we call mechanical alloying, which we will talk later. In fact, it is just ball milling. Mechanical alloying is basically bringing dissimilar metals, that means more than one element brought together, and then you induce alloying into it. So like that, we can again generate either nanocrystals, quasicrystals, glasses, or any other metastable structures, or for that matter simply just refinement of microstructure. You want a microstructure not to have 100 microns grain size, but you want 10 microns grain size, one can also achieve that. There are some applications where you want oxide powders, for example paints. Think of paints. Paints, you need fine powders. There people are interested if you can bring down the powder size to 1 micron, that's enough for them, for most of the applications. So you need not have to really go to nano. But for such applications, just you need to somehow make them to that. Either you can do it from the solid state, or if it is possible to melt such a material and then cool it rapidly, you can get such fine microstructures even by what is called rapid solidification. So this is the technique which we will learn, and what is the basic principles behind this technique and what kind of advantages we gain by this technique. Before we go into that, let us just look at the origin of it. As I must have mentioned it to you some time back, the origin basically goes back to 1959, when a person by name Paul Dewey had looked at the silver copper system. We have talked about this probably at some point of time when we were talking about glass formation. And so this is a system, silver copper system. If you take silver, gold and copper, gold and silver, copper, if you look at these three systems carefully, these three systems, the silver gold and copper gold are isomorphous. These two are isomorphous, whereas silver copper is a eutectic system. For many years people did not really understand because it disobeys the Hume-Rothery rules. The Hume-Rothery rules we know, which were 1930s onwards, people know about them very well, that the solubility of A in B is decided by certain 4 factors: size factor, electronegativity, valency, structure. These are all the things which we know. Whereas here is the case where all the 3 elements have similar structure, they are all FCC, their atomic sizes are very close to each other, their electronegativities are very close to each other, but still 2 systems among these 3 components will form isomorphous as expected from the Hume-Rothery rules, whereas the third system does not follow. So then Paul Dewey thought, if I can take this particular liquid and then cool it slightly rapidly, it's possible that I may be ending up with a solid solution. So that means if you take that phase diagram, this is the typical phase diagram of silver copper. What is the melting point of copper? 1083, and that of silver 963. Okay, so silver is slightly lower, about 100 degrees lower than that of copper. So if you look at the phase diagram, the solubility of silver in copper at room temperature is approximately about 10%. This is silver on this side and copper on this side. Similarly, copper in silver also almost the same, 9%, 10%, that is the range that you get. So if you look at this, this is definitely not isomorphous, it is a eutectic, you can see that. So what he thought is, if I take this eutectic alloy, if you solidify it under equilibrium conditions, what should be the microstructure of this alloy at room temperature? Can you tell me, Amini? This alloy, that eutectic alloy, if I solidify it under equilibrium conditions at room temperature, what will be the microstructure? It will be alpha plus beta. Alpha, beta, if you think of it here, it will be alpha plus beta. Only problem here is we usually do not refer to these as alpha and beta because both have same crystal structure. It's like alpha dash, alpha 1, something like that, or alpha 1, alpha 2 people refer to as, because both are FCC. So anyway, so there is 2-phase mixture, alpha plus beta. And so if there is a 2-phase mixture and if you do an X-ray diffraction of such an alloy, what will be the typical nature of the X-ray diffraction? What do you observe in the X-ray diffraction? That's it, simple. You will get peaks from alpha, you will get peaks from beta. Interestingly, that alpha and beta being the same crystal structure, both are FCC, you will have the FCC peaks of both, but the only difference would be that if you look at the XRD pattern, and if I, so two peaks of FCC, 111 peaks, 111 of let us say silver. At the moment we still do not know which one will have a lower theta, which one will have a higher theta, let us not bother about it, but you will have two 111 peaks of silver solid solution, you call it as let us say silver based solid solution, you call it as alpha, let us say, and copper based solid solution if you want to call it as beta. Usually in metallurgy beta is reserved for BCC structures, so we do not use usually here beta, so we usually refer to them as alpha 1 alpha 2, because alpha is for FCC, beta is for BCC usually. So anyway, for that it does not matter whatever is the notation. So what you see is that two peaks of one solid solution and another solid solution you will find, and then you will have the 200 peaks, again one of 200 peak of alpha 1 and 200 peak of alpha 2, and so on. And if the lattice parameter difference between these two is very close, then what you would see is simply that instead of two peaks like that, you will see this kind of nature. You will see a shoulder in each peak, indicating that the lattice parameters of both are so close that they overlap with each other, and this means that there are basically two peaks, one corresponding to alpha 1 111, alpha 2 111, and alpha 1 200 and alpha 2 200, and so on, 220, 311, so on. So what you can clearly see here is you will definitely get the peaks corresponding to both the phases, and that is a signature of a two phase mixture always. So what he thought is, if I take this alloy and then solidify it rapidly, what is that I am going to end up with? So he took this alloy, and what he did was using a technique called gun quenching. What he basically did was to take a crucible with a small aperture at the bottom and then close this aperture with some kind of a metallic foil, very thin metallic foil, and then put the silver and copper into this and melt it. So you have the liquid of silver and copper into that with the eutectic composition. And what you do is, once you think it is molten, you introduce argon into the system, pressurize this liquid with argon, and when you pressurize this liquid with argon, what happens is the liquid immediately pierces that foil and then falls onto a copper block which is kept below. You know, copper has a very high thermal conductivity, so as a result, if you put a copper block and allow this liquid to, it's like a gun, you are piercing the foil through a high pressure argon gas, so like a bullet it comes out. In fact, you can hear the sound of the piercing, and then it comes out, the liquid comes out like a bullet and falls on that. So at a very high rate, high velocity, and once it falls onto that, obviously whenever a liquid droplet falls onto that, it becomes like a flake, a thin flake. So you will have a large number of this kind of flakes falling here. You will never get a continuous ribbon here. A large number of flakes just fall on the floor there, and you just collect these flakes and then try to do an X-ray of these flakes. And if you do an X-ray of these flakes, interestingly what he saw was that he saw just peaks like that, just single peaks of 111, 200 and so on. Instead of getting the peaks like this, what we saw before, he now got peaks like this with slight broadening, suggesting that the grain sizes are much finer here. And why does this whole thing happen? This happens because of two reasons. One, there are two aspects which take place here. One is what is called grain refinement. As I might have told you before, grain refinement during rapid solidification is related to what? Is related to the undercooling. Okay? So we have seen that if the cooling rate increases, then the delta T increases. There is a direct correlation between the cooling rate and the undercooling, because as you are cooling it faster, the liquid does not want to solidify at the equilibrium melting point because of the inertia in the system, and so it gets undercooled to below the melting point and then starts solidifying, and because of which you will see that there is something called an undercooling. And the higher the cooling rate, the higher will be the undercooling, because the higher will be the inertia. You are not providing sufficient time. As you are increasing the cooling rate, the time available for the nucleation to occur is very small, isn't it? And if the time available for the nucleation to occur is very small, you have to really undercool it to very high low temperatures. In fact, this is not really true up to a very large undercoolings, because we know this TTT diagram. Let us imagine that there is a liquid here, there is a solid nucleation. This is the standard temperature time diagram which we all know about it. When we talk about austenite to perlite, we talk about this regularly. So if you look at this, you can see from here the time required for the nucleation or for the start of the solid formation keeps on decreasing like this as the temperature decreases, isn't it? So you need lesser and lesser time as you come to lower and lower temperature, and that is what we call the incubation period. So when you are cooling rapidly the liquid, because the time required, time available is very small. For example, let us say you take a liquid and rapidly cool to this temperature, and if the time that you are allowing is very small because of that cooling rate at that particular temperature, at any temperature we can calculate what is called residence time at any temperature whenever you are cooling it very rapidly. So basically the cooling rate divided by the temperature, if you do it, basically you get some time, temperature divided by the cooling rate, then the time goes to the numerator. So you will get that what is called residence time. If that residence time is smaller than the incubation period, then there will be no solidification. So what will happen is that liquid will not undergo solidification at that temperature, but liquid will cool further and then come to such a temperature where the time that you are allowing is equivalent to the incubation period. At that temperature it will start solidifying. So if the cooling rate is higher and higher, because you are providing lesser and lesser time, so it will keep on going to lower and lower temperatures up to this nose temperature. In fact, if the cooling rate is much higher, then even this solidification will not occur. Then you will come to a situation where you will hit the TG and get the glass. So as long as your cooling rate is below the critical cooling rate, you can see clearly, if I use this liquid and draw different cooling rates, you can see from this, for this cooling rate, let us say call it 1, 2, 3, 4. You can see from 1 to 4, is the cooling rate increasing or decreasing? It is increasing, because the slope of this line is nothing but the cooling rate. So as you are increasing the cooling rate, you can clearly see here the delta T is automatically increasing. If you look at where this cooling curve hits the start of transformation, that will tell you what is the temperature at which transformation is happening. If your cooling rate is very slow, very slow, that means if the cooling rate is very slow, then the transformation will occur at the equilibrium transformation temperature, which is nothing but the melting point. That is what we call the equilibrium transformation. When the cooling rate is very slow, which is called equilibrium cooling rate, equilibrium conditions, then the transformation will occur at the equilibrium transformation temperature. Otherwise, if the cooling rate is higher, so the higher the cooling rate, the higher the undercooling. So you can see there is a direct relation between cooling rate and undercooling, because this is the temperature at which transformation is occurring at these cooling rates, and higher undercooling, the transformation is occurring at a lower temperature, and delta T is nothing but the equilibrium transformation temperature minus the temperature at which transformation is taking place, and that becomes larger if the cooling rate is larger. So as a result, we know that if the cooling rate increases, delta T increases, and if the delta T increases, we have already seen before that the delta G increases, which is the driving force, and if the delta G increases, we know the R star decreases and the delta G star decreases, and finally the I increases. All these are connected. There is a chain of events that take place once the delta T. Everything is related to just one parameter, that is the delta T. That is why undercooling is crucial in, that is why people say nowadays after almost now how many years? More than 45 years, let us say close to 45 years after rapid solidification has started, 1959. Now people know that you need not have to even cool it rapidly. If there is any way to give high undercooling to the liquid without cooling it rapidly, you can get all the advantages that you can achieve with high undercooling, with the rapid solidification, by just giving high undercooling. Have you heard of any such techniques? How do you achieve high undercooling without cooling it fast? Bulk metallic glass is yes, including inoculation. No. If you are putting inoculation, it is a heterogeneous nucleation. Okay, so heterogeneous nucleation will only make the grain size smaller. It will not give you high undercooling. In fact, it will decrease the undercooling. If you think of the cooling curve, This is the typical cooling curve for a homogeneous nucleation, and for a heterogeneous nucleation the cooling curve is either very small like this, or sometimes it will be just like this, because you are providing the substrates, so undercooling does not take place. The way to do is not pressure. That is what he said, bulk metallic glasses, putting large number of elements, but that has nothing to do with undercooling. That is only makes the nucleation more difficult of solids, and as a result you get a glass. That is only to make a glass, that is not to make undercooling higher. So here what you do is, when does, under what conditions the undercooling gets reduced? It is by inoculation, as he has pointed out, Nirupam just now. So the way is the reverse, remove the inoculants. If you can somehow remove any heterogeneous nucleating sites inside the liquid, then the liquid has no other solution but to get undercooled to very low temperatures, up to what is called homogeneous nucleation temperature. That is what people do by what is called emulsification of the liquid. Droplet emulsion techniques they call it. Emulsion techniques. What they do is, they take liquid and immediately emulsify the liquid. How do you do that? There are different techniques. One is atomization. Okay. What you can do is, you allow the liquid to fall through a nozzle and then inject a gas to that, so that the liquid breaks and then becomes very fine droplets. And now if you look at these fine droplets, there is a possibility that some of the droplets will not have any heterogeneous nucleating sites. The point is, whenever you melt a liquid, there is always bound to have some kind of inclusion particles, unless you really do under very highly controlled conditions, vacuum, and you have some waste. For example, you must have heard of secondary steel making. Just to remove inoculants, it is a very tough process. They go through a number of techniques, vacuum remelting, electroslag refining. There are so many techniques people use just to remove inoculants, because there are some steels where the inoculant percentage has to be kept very low, because we know that these presence of these second phase particles are the ones where the crack initiates. So you don't want such a thing to happen. So for some strategic applications, people give in the design parameters itself, the inoculants what are called second phase particles, or the oxide particles should not cross a particular limit. So as a result, you have to refine to remove these. There are techniques to do that. So here what you do is, you just emulsify the liquid, and as you decrease the particle size of the liquid, droplet size of the liquid, the probability of finding a particle inside the droplet obviously decreases. The bigger particle can have more particles. A smaller particle will not have more particles. I mean, may not have particles. So if you look at these solidified particles, people have seen the smaller particles are the ones which have really solidified at high undercooling. How do you know that they have solidified at high undercooling? Is there any way to find out? This is like a post-mortem, like failure analysis. After the thing has happened, you try to find out what is the cooling rate, or you try to find out what is the undercooling, because there is no way to directly find out, measure the undercooling in a droplet. How do we find out? We look at the microstructure. There has to be some correlation of the microstructure to the undercooling. Particularly, if you look at the what is called the eutectic microstructures, let us say, or if you look at the dendritic microstructures, The interdendritic spacings are the what is called the secondary dendrite arm spacing, SDS people call it, dendrite arm spacing. That means if you look at a dendrite, okay, this is like a typical dendrite, let us say. So, this spacing between these two is called dendrite arm spacing, DAS, people usually measure, and this dendrite arm spacing is always a function of the undercooling. The higher the undercooling, the higher the nucleation rate and the smaller the R star, and because of which this decreases. Similarly, if you look at the eutectic microstructures, if you take a eutectic composition and then try to solidify, the what is called interlamellar distance. You know, whenever there is a lamellar eutectic that forms, the interlamellar distance between any two. For example, if you look at the perlite, which does not really form from the liquid anyway, we should not consider that. But if you take any simple microstructure such as aluminum copper is a dendritic is a lamellar eutectic. So you look at alpha beta, this kind of a eutectic microstructure, and this distance between any two alpha is what is called interlamellar distance. The center of the one alpha lamellae and the center of the another alpha lamellae. So if you look at the alternating alpha lamellae and look at the distance between them, that will give you what is called interlamellar spacing. And this interlamellar spacing and this dendritic arm spacing are directly related to undercooling. So there are actually a number of experiments people have done, and we already have a lot of database on what is the correlation between these two. So from that, if you measure the actual the DAS or the actual interlamellar spacing, one can go back, calculate what should be the cooling rate or what should be the undercooling. Cooling rate is one way, as I told you, basically it is the undercooling. And there are methods to measure also. For example, there was one technique which people have used, what is called drop tube technique. Have you ever heard of this? Have you heard of containerless solidification? So where people electrostatic or electromagnetic levitation they do. So they take a metal a piece, it has to be very small, otherwise it's very difficult to levitate because of the weight. So you try to apply some electrostatic forces or electromagnetic forces so that that piece is levitated. That means it floats into in the atmosphere, and then through laser or through some kind of a heating means you melt it. So it is floating and then it melts now. There are a number of experiments people are doing on this. And now if you allow it to solidify, that means you allow it to cool, remove that heating source. People can melt it through laser, electron beam. There are many ways of melting such levitated particles. Now if you allow it to cool, there is no container inside which this droplet is solidifying now. So once there is no container, then there is no heterogeneous nucleations. Usually we know whenever you pour the liquid into a mold, the mold wall itself acts as a nucleating site. So here there is no mold wall, nothing. So the liquid droplet now solidifies. Just keep on observing. People can put thermocouples, or obviously thermocouple cannot touch the sample. So you can have optical pyrometers and measure the temperature and try to see how it cools as a function of time, and then plot what is called the cooling curve. And if you plot the cooling curve, you can find out to what temperature it has really undercooled. So you will get this kind of a cooling curve. if it is a pure metal. And from that one can really measure what is the undercooling. And then if you look at the microstructure of that and correlate now the undercooling to the microstructure. So like that people have, this is one technique, levitation is one technique people have used. Another technique is what is called drop tube technique. What they have done is they have taken long drop tubes, 100-meter drop tubes are available. In fact, there was a proposal to have a drop tube in IIT Kharagpur. Our main building, the old building, people wanted to use it as a drop tube. That means you put a furnace on top and then allow the metal to melt, small piece of metal, allow the liquid to drop in a tube up to the bottom, and when it keeps on dropping there will be a condition. This has been done not just for finding out what is called the undercoolings, but to understand what happens under microgravity conditions. There is a lot of research going on about microgravity. We know one of the major problems in solidification is what is called segregation. If you are melting two elements such as lead and let us say copper alloy, lead has a much higher density than copper. So when both of them are solidifying, the alloy is solidifying, there is always a tendency for what is called gravity segregation, isn't it? So because of which the composition is not uniform throughout the sample. And we know that that kind of a situation can be completely removed if you have a loss of gravity. That means if you have a zero gravity condition. And people are doing experiments on the International Space Shuttle, ISS they call it. And in addition, a number of people who try to simulate such conditions on the earth using this kind of drop tubes. For example, I don't know whether you have heard of, if you go in a lift, keep on falling in a lift from a very high, particularly in places like abroad. I have seen places like in Japan where 98 floors, okay, from there if you are falling, you will definitely experience a few microseconds of microgravity condition. So it's like that. So many people are studying that and try to see what kind of different microstructures that you get. Similarly, for example, we talk of inoculation. Inoculation has something to do with interfacial energies, isn't it? We know that the interfacial energy between the inoculating particle and the solid is much lower. That's why the solid is nucleating on the particle. How is this going to be affected under loss of gravity? Whether the interfacial energies have something to do with gravity or not. These are all mostly academic research, frankly speaking. The number of people who object to them. But then NASA is doing a lot of research on this. One of our own faculty members in IIT Kharagpur, Professor Dhinda, does a lot of research in collaboration with NASA on this microgravity. So what kind of microstructures are developed under microgravity and how to generate microgravity, that is one aspect. And what is the science of solidification under microgravity conditions? How does solidification occur? Particularly when a composite is solidifying, what kind of a microstructures are generated, whether the particles are pushed to the grain boundaries and you don't get a uniform distribution, or whether the particles are engulfed, what kind of conditions that happen, and what is the rate of solidification under microgravity conditions when compared to normal conditions. So a lot of research is going on. One such aspect is the undercooling. So in the drop tube, when you keep on allowing the particle to fall, which is nothing but a containerless solidification, the droplet is just falling without any container. So it will at some point of time, and at various heights people put thermocouples to measure the temperature of this droplet that is falling. That means you put pyrometers. Obviously you cannot put thermocouple which touches that particle, you put optical pyrometers and put pyrometers and measure the temperature of the droplet and find out at what temperature it has started solidifying. And then from that deduce what kind of microstructures you have got. After the particles has really solidified, what you do is just to cut the particle. Cut the particle, look at the microstructure, and you can identify what is the microstructure, what is the dendritic spacing, or what is the interlamellar spacing, and from that you correlate it to the undercooling. And different type of particles, different sizes of particles will have different undercoolings and will have different microstructures. So ultimately correlate the microstructure to the undercooling and correlate the microstructure to cooling rate if people do fast cooling experiments. So fast cooling is one technique, but because we know fast cooling basically gives you high undercooling, even if you don't do fast cooling, if you just have high undercooling possible, but this kind of high undercooling can be achieved only in special conditions. For example, levitation is not a condition which is easily possible for large quantity of materials. Similarly, if you want to do droplet emulsification, that is one technique which is not very difficult, but the point is different particle sizes will have different undercoolings. For example, atomization, if you do atomization, liquid is atomized by a gas. You have this kind of a nozzle, liquid is here, the liquid is allowed to fall, and then you have a jet of gas, allow it to fall on that liquid which is falling. So immediately the liquid gets emulsified like this, becomes droplets, but you will have different sizes of droplets. But one can do a lot of engineering on that to control narrow down the size range. There are a lot of people who are doing. DMRL is one place where a lot of work is going on that. And atomization is a standard technique to produce powders, metallic powders. Most of the metallic powders are produced by atomization. This is a standard technique. So in that, but most of the atomization techniques that are used are for sizes which are of the order of around 100 microns or more than that, 50 microns. People do not really go to less than submicron size. When you really go to submicron size, that is when you will really see the particles without having any inoculants, and that's when you can really achieve very high undercoolings and achieve novel microstructures. So if you achieve high undercooling, what are the things that you can get? One is, as I just now pointed out, yes, here. One is this, that R star decreases and I increases. That gives you what? Grain refinement. That is one of the whole story. It is not the complete story. So you can get grain refinement or microstructural refinement. Grain refinement is in case of pure metals, okay, but most of the engineering materials are not pure metals. You use alloys, many times multi-component alloys. So you want microstructure refinement. You want the grain size, or if it is a eutectic microstructure, you want fine interlamellar spacing, because you know that if the interlamellar spacing decreases, the mechanical properties increase. We know this. There is a direct relation between this. And similarly, if you have a two-phase mixture, you want fine precipitates to be uniformly distributed. So all this refinement of microstructure is one way which can be achieved by undercooling. Second thing is what is called extension of solid solubility. This is another advantage of rapid solidification processing. And why do you get this? This comes again because of high undercooling. Whenever you have high undercooling, we have talked about T0 curves in the thermodynamics class. So it is all related to the T0 curves. Let's look at one example of a T0 curve. So if you look at a eutectic phase diagram like this, with a T0 curve which goes like this, let us say, this is T0 for alpha, this is T0 for beta, T0 alpha. If you look at these T0 curves, if I am cooling it rapidly, I am providing high undercooling. If I am having a undercooling, let's choose a composition like this. If I choose a composition like this, if I can undercool below this T naught, then definitely there is a driving force for what is called partitionless solidification. We have talked about this probably some time back. It is also called polymorphous solidification. But mostly the partitionless solidification is the regular term that is used, because polymorphous transformation can be used for any type of transformation. What is a polymorphous transformation, Yamini? Where the composition remains the same and the structure changes. That is a polymorphous transformation. Where only structural change is taking place, that is why we say polymorphous. Morphous is structure. So structure changes. Structure changes from one to the other. Here what is the change? It is changing from a liquid structure to a crystalline structure, but the composition remains the same. That is a polymorphous structure.
Is there no difference between polymorphous and polymorphic?
Polymorphic transformations, people, same thing. Polymorphous transformation, polymorphic transformation, just the same. It's only terminology. Okay. So this is nothing but the partitionless. Partitionless means there is no partitioning of the solute into the liquid and the solid. Usually whenever you take this liquid, under normal conditions what happens is the moment you reach this temperature, solidification starts under equilibrium condition, and you will see a solid having this composition comes out. And if you come to a lower temperature like this, now liquid will have this composition, solid will have this composition, isn't it? The solute, if you call this as C0 composition, that C0 is getting partitioned between the liquid and solid. Solid will have CS composition, this is CS composition, let us say, I bring it down and call it a CS, and this is composition is called CL composition. So the C0 gets partitioned between the CS and CL, and in principle we can draw the what is called the mass balance equation, which is nothing but the fraction of the solid multiplied by the composition of the solid plus fraction of the liquid multiplied by the composition of the liquid should be equivalent to the C0. That is nothing but what is called the mass balance equation, from where we derive what is called the lever rule, isn't it? So this is under equilibrium conditions, but if you cool it very rapidly under rapid solidification conditions, you come to below the T0. If at all you come below the T0, then there is a possibility for partitionless solidification. That means liquid having C0 composition will transform to solid having C0 composition. And we also talked about what is called hypercooling during our thermodynamics class probably. That hypercooling tells you what is the critical cooling that is required. The delta T hypercooling is nothing but the critical cooling undercooling that is required for having partitionless solidification, which is equivalent to delta T naught plus delta T recalescence, where delta T naught is nothing but T liquidus temperature minus T naught temperature for that composition. For a particular composition, for example this C0 composition, T liquidus temperature is what? This is the T liquidus temperature. T naught is this temperature. So this difference between these two is delta T naught. And what is delta T recalescence? Is nothing but delta H fusion divided by delta Cp, because we know that delta H is equal to integral delta Cp dt. and we can write always that delta H equal to delta Cp delta T. So delta T is equal into delta H by delta Cp. What is this recalescence? We know that when a liquid gets undercooled and a solid is nucleated, the moment solid is nucleated there is a heat which is released, and once the heat is released, the liquid which is surrounding that solid which has nucleated, its temperature will go up, and once its temperature goes up, and if it goes into the regime above the T naught, then obviously partitionless solidification cannot occur. As a result, you need to be below the T naught temperature for that particular composition even after the recalescence has occurred. So if you want to make sure that this happens, it can happen only when this difference between these two is also considered, and then if the total undercooling is equivalent to these two. So this is what is called extension of solid solubility, because if you can undercool a liquid up to the T naught, definitely you have been able to achieve a solubility which is equivalent to this much. Liquid of C naught composition has solidified into solid of C naught composition, whereas the actual equilibrium solubility at room temperature is only this much. Now your solubility is this much. So this is the extension of solid solubility. So you are able to extend the solid solubility. What is the advantage of extension of solid solubility? Yes. You can get solid solution hardening, you can get precipitation hardening, extra precipitates you can get. Volume fraction of the precipitates can be more. So that is another way. Then what is the other advantages? The other advantages is you can get metastable microstructures. Metastable, they can be crystalline microstructures, there can be quasicrystalline, there can be glasses. That means when you undercool the liquid very rapidly to very high undercoolings, at that high undercoolings, once you are at a very low temperature, at that temperature solidification is occurring, then there is a competition between the equilibrium solid that is coming out and some other non-equilibrium solids, and if the non-equilibrium solid has a lower activation barrier, that will form more easily than an equilibrium phase. So as a result you may have non-equilibrium crystalline structures which may not exist in the phase diagram. For example, as I must have mentioned to you many times, when we are doing edge hardening, instead of the equilibrium structure, some other non-equilibrium structure comes out. For example, aluminum copper, instead of the theta double prime or GP zones, they do not exist in the phase diagram, but they come out. So like that, during cooling also, if the activation barrier for such phases is lower, so you may get such metastable phases, and you can get quasicrystalline phases, and if the cooling rate is still faster, you will end up in glasses. We have talked about all this before. So with this we will stop and then we will continue in the next class. Thank you very much.